start this lecture with a thought process from William Ramsay. He says the country which is in advance of the rest of the world in chemistry will also be the foremost in wealth and in general prosperity. I would like to draw your attention to a book which is basically known as Hindu Chemistry it was written by P.C. Roy long time back, right. If it is there in Google, you can see and then look at it. So, we are basically discussing about reaction rate coefficient or the specific reaction rate in the last lecture, and we have derived it, and we have also looked at how one can use the collision theory to do that, and considering the molecular theory of gases. And we will now dwell more on that, that is basically what we look at the K. If you look at K, we have looked at this is small k. K is basically A e power to the R u t, and K is not a constant, K is a function of temperature, right, and K is basically function of temperature. I can write down K is a function of temperature, right, and A we call it as a sometimes pre-exponential factor is basically a constant. Is it really a constant? It is not. Okay. So, if you look at the this thing, you will find out that it is basically A n A. If you recall, A is A n sigma A b square 8 k b by there will be pi m relative into half into steric factor into T power to the half. This you can consider till this, okay, you can consider as what? As a constant, because steric factor is a constant for between molecule A and B, and Kb is a Boltzmann constant, and Mr relative mass is also a constant, right, and sigma Ab already like molecule we are considering constant. But however, T is power to all. So, I can write down this is basically B, right, which is a constant into T power to the half. So, therefore, I can write down K T is equal to B T power to the half E by R u T. We will be discussing little bit about this little later on. I will show you how it can be, but problem is this kind of expression for K what we have derived, right. If you consider this portion, it does not really tell us to how to evaluate the steric factor, okay, and how to evaluate the activation energy, right. So, these are the limitation of that, and for that of course, there is a very sophisticated theory what you can look at it using this quantum theories, and people have talked about it, but I will not dwell much upon that. But I will just like to mention that people have talked about activated complex theory, right. This is basically activated complex theory. It is given by Eyring, right. I will just touch upon it. It is a very complicated, I will not get into, but what it says, it assumes, right, there will be an intermediate activated complex which will lead to the product, right. That means there is a transient state of the reactants which can lead to decomposition of a product of a molecule into its product, right. For example, if I consider that let us say hydrogen iodide, right, H this I, plus I will consider another hydrogen iodide, okay. It can go to, this is basically reactant, right. When they will collide each other, right, what will happen? This may coming like kind of things, and I, and this is the activated complex. It is leading to H, right, one molecule plus I, this is your product. That means this of course gives a physical meaning to that of the activation energy. And if you look at, if I can write down that reactants, right, is getting to activated complex. Keep in mind that even though it is going to activated complex, it may return back to the reactant and then it will go to the product, right. The activated complex can get into this side, product side, but once it will get into product, it cannot come back unless there is another collision, okay. Are you getting? So, therefore, this is the way it can be really look at it, that activation energy is required to take initial system to the activated complex. So, what I was telling, that is basically reactants, you know, you will be having, it will be having much higher energy level, activation energy means much higher energy level than the average energy molecules will be possessing, right. Then only it will be collision, then it will get into activated complex and then it may return back, I am like nothing there, okay fine, but otherwise it will go to the product, and this kind of reaction is basically exothermic reaction. Endothermic reaction will be other way around, the reactant will be here somewhere and product will be somewhere up like higher energy. So, that is the endothermic. So, it will be true for all the things, right. Now, if you look at this K values, right, I mean this is the reason I thought I will get into this, but some of you may be interested in that, get into this activated complex theory by Eyring, who is happens to be a Nobel laureate, and which is little complex. I will not deal with that. This is the specific reaction rate constant. Keep in mind that generally people talk about these things in from Arrhenius form of relations, because from the experiment Arrhenius really found out the values of E and Ru, right. So, what I was telling, this Kt is basically B T half into e power to the RUT, and this you can get these values, you know, this is basic you know pre-exponential factor, generally this is in Arrhenius form, this A is known as pre-exponential factor, but for elementary reaction if you want to look at it and also take care of the T what you call coefficients, this is A, and this need not to be half all the time for elementary reactions, right, where you will conduct experiment and do that, and this can be basically K T is equal to B T power to the let us say N e power to the RUT. I will show you some of the data for hydrogen oxygen system, right. If you look at, this is what I was writing B, right, this is nothing but your K T is equal to B T power to the, I am sorry, that will be B e power to the RUT. So, these data are given, B is corresponding to these values. Let us say if I take H reacting with oxygen getting into OH plus O, and B is basically 0.91 and E is your activation energy 69.1 kilojoule per, and this is in the range of 300 to 2500 Kelvin. That means this will be valid for that, these people have got. Keep in mind that when you are reacting other way around, OH plus O going to the O2 plus O, basically this is the same reaction in the opposite direction of the first one, but however the B is different, quite different. Of course, the capital B, small b is 0, right, and this activation energy is 0, right, and this is again in this range. And of course, these are the various reactions I have shown here. Keep in mind that in this reaction particularly, the M is the third body reactions, and it will be hold good for low pressure, it will be argons, right, and hydrogen or any other stable basis. And sometimes this B also will be negative, right, okay, it will be also negative, it need not to be this thing. And of course, there are various reactions. Keep in mind that all these values B and E, and generally people conduct experiments particularly for the forward reaction whenever possible, and then they calculate from the equilibrium the backward reactions. Okay. Therefore, sometimes E is coming 0 and this thing, number one point I want to make. The other things I will talk about is that these numbers, you know, if you look at two people are conducting experiments, there might be 10 times different than the number. The error, you know, will be something 10 times. That is why people jokingly say, oh, this is a thing whatever you put, and we do that for a global kinetics. You know, what we will do, we want to match the reaction rate or the heat release rate, we will be playing with these B values or the particularly a pre-oxidation factor, and then try to match. That is the another way. Activation energy, generally the error, you know, experimental error will be order of something 10 to 30% error. Sometimes, you know, if you look at, that is the thing with which we are living today, maybe in future it will be improving on, right. So, as I told, although we related this pre-exponential factor and exponential factors into the kinetic theory of gases or the collision theory, but people do conduct experiment, and there is a Arrhenius form of reaction, right. What it is basically, if I write down, this is dC A by dt is nothing but A, right, e power to the RUT into CA CB. Basically, this portion is known as Arrhenius form of reactions. Now, if I take the log of this, right, this, if I take a log, what I will get? I will get ln k is equal to ln A minus e power to the E by RUT, right, right. So, and if I will take this and plot these values ln by 1 over t, right, I will get a slope E by RU, right. If you look at from this slope, I can get E by values, right, and if I will get these values here, what I will get at this kind of thing, I will get basically A, right. And from this one can really find out from experimental data, you can put it and then get these values slope, and then get these values A, and then you will find out what it will be, right, because this is corresponding to that. Now, if there is a pre-mixture like methane is reacting with oxygen is going to CO2 and water, right, then I can write down CCH4 is equal to CCH4 CO2 into A E by RUT, right. Are you getting? By dt, this is negative. Now, if I put this reaction rate, and that is nothing but a reaction rate, this is reaction rate, and I will plot it, I will get reaction rate versus temperatures, because temperature is the function, right, and particularly but certain fuel air mixtures, right, which is pre-mix, let us say, then what will happen? The reaction rate goes on increasing, because temperature is increased, that will increase, right. And once this methane or the oxygen, any one of them, right, will be coming to the 0, what will happen? It is moving here and the reaction rate will be coming down, drop, and this is corresponding to the, like your maximum activation energy, what will be happening, right. So, this will be coming to 0, because why? Any one of them species is tending towards 0, not 0. If it is become 0, then it will come to the standstill, even though temperature is higher, but reaction rate will be 0, because this is 0, getting into 0, right. So, that you should keep in mind, and otherwise if reaction rate is not if it is not finite, infinite fuel air mixture is there, this will be reaction rate will be going up as the temperature increases, right, for a particular activation energy. So, now this what you call the form of equation, what we have seen is basically the Arrhenius law, what they call, that is K is equal to A RUT, right. And this can be, keep in mind that it is basically at a high temperature the slope will be higher, and low temperature it will be slope will be low, right. That is a reaction which will taking place. Keep in mind that this is from one experiment, right, and this maybe you can get experiment number 2, means type, one, this is experiment number 1, this is experiment number 2. There might be some common, then which one is that? That is the one you should not worry about, because these are two different experiments from where you are getting data. Now, let us look at how does this reaction rate vary with temperature, right. If I consider this reaction rate Ca, of course, there is a coefficient and Cv coefficient. This is in our case we have taken A as 1, B as 1, okay. Are you getting? If I write down as basically what you call, if I write down A plus B, B going to C, C plus D, then this will come into picture. This A is the stoichiometric coefficient, right. And if I look at reaction 2 and reaction 1 corresponding to two different temperature T1, T2, I mean all are same for the same reaction, it will cancel it out. So, you will getting E by RUT, and keep in mind that if there is a 10% increase for the same activation energy, the reaction rate will enhance by almost 100%, right, kind of things. So, but the limitation of this Arrhenius is that it cannot simulate combustion process over a wide range of temperature, as I have explained, right, and rate law matches well with experimental data at high temperature, but not at the low temperature, right, not at the, in this low range, this kind of things may not be look at it, right. For the same experiment, if we will do in the different temperature, you will get a different slope. So, therefore, one has to be little concerned about that. But if it is just, if it is both the experiment are different, then that is all right, but if it is the same reaction and you are only changing the temperature, getting two different slope, then therefore, one has to be careful. Yes.
Sir, A will also depend upon temperature.
A? Here in this case, Arrhenius form of reaction, it does not recognize that as a function of temperature. But whereas when you go to the elementary reactions, right, it will be recognizing T is a function. See, as I told, this is a Arrhenius form. Arrhenius form does not, as I told earlier, A is equal to B T power to the some coefficient, right. But in this case, Arrhenius does not recognize that as that, because from experiment it will be difficult, like then there is a put into a ballpark number, That is the difference between Arrhenius and the elementary reaction rate coefficient. Are you getting? So, let us take an example, right. A vessel contains 10 power to minus 6 moles per centimeter cube of nitrogen oxide at 650 Kelvin, and which is decomposed as per the following reaction: 2NO2 is going to 2NO plus O2, and specific reaction rate at 650 Kelvin is 770 centimeter cube mole per second, right. And we will have to determine basically activation energy if its specific reaction rate becomes 400 Q at 600 Kelvin. Basically, what is given at two different temperature, the reaction rate is given, right. So, we know that K1, right, at temperature T1, right, at temperature T1 is 650 Kelvin, right. We know the what is that reaction rate, K is equal to A T, right. This is the reaction rate, and at this one if I take the log, this will be ln K1 is equal to ln A minus E by RU T. So, at T is equal to 600 Kelvin, the reaction specific reaction rate I can take is as a K2 is equal to ln A minus E, this is by RUT 2, right, and in this case this will be 1. So, if I say this is equation A and this is equation B, right. So, if I will take just minus that one, that will be this and this will be plus, this will cancel it out, and that I will get, right, if I say equation A minus equation B as ln K1 minus ln K2 is equal to what you call E by RU. If I take, this will be 1 by T2 minus 1 by T1, right. So, if you look at in this I can say this is equation 3, K1 is known, right, K1 is given, K2 is given, E is given, E is given or not? E is not given, you will have to find it out. RU is not, T is given, right, T2 is given, T1 is given. So, you can find out activation energy. So, activation energy becomes T1, T2, T1 minus T2 RU ln K1 by K2, right. If I substitute these values, I will get T1 is what, 650 into T2 is 600 into 8.314 divided by T1 is 650 minus 600 ln 770 divided by the 400. You will get something E is equal to 42.5 kilojoule by mole. So, you can get very easily this activation energy, and keep in mind that people do these things routine manner to find out at two different temperature what will be the activation energy, right. And as I told, the slope will be the your activation energy, you can plot several data and you can get. So, with this I will stop over, and then we will see in the next lecture about more about the elementary reactions.